I'm Karol Desnos, and today I'm going to present the work of my 10 last years of work for the habilitation defense. And the work is entitled Design Automation and Multi-Objective Optimizations for High-Performance Embedded Systems. Okay, so how did I arrive here? It doesn't work, of course. Yes. Okay, so I was born in 1988, and after a completely irrelevant series of events, I obtained my PhD in 2014, in September, to be exact. After that, I obtained an assistant professor position at INSA Rennes in September 2014 until September 2015. Then I was a research engineer for a few months, and finally I became a maître de conférence, associate professor, still at INSA Rennes from December 2015. And all of these appointments were joint appointments with the IETR laboratory. Okay, but what did I work on? So oh yes, and this brings us to the habilitation defense of today. What did I work on? My main research focus is about embedded system design and more precisely about cyber-physical systems. So what is a cyber-physical system? The cyber-physical system is a computing platform that will interact with its physical environment. So it will receive data from the environment through a set of sensors and data, for example, from time or light conditions or user data. And it will have the ability to interact with this environment by acting with some actuators. And nowadays, such systems are so interconnected with internet through communication networks. And this gives them the possibility to bring them to offer intelligence service, connected intelligence service.
Marilyn, yes. She's just connected. Yes. Just to let you know. Okay, sorry.
Welcome, Marilyn. And okay, where do we find this kind of a system? We find this kind of systems everywhere nowadays. And especially we find them in advanced driver assistance system, in e-health system, in Industry 4.0, or in smart anything, smart homes, smart cities, smart grids, and all of this kind of system. What is inside the computing platform? If we have a look inside the computing platform, we can see the embedded system stack, which is usually composed of a hardware and a software part. At the lowest part of the system, we have the computing substrate. This is where the computation is happening. This is what we build. This is what is getting out of the factory. Then right above that, we have an abstraction of the hardware. This abstraction can be used, for example, to simulate the behavior of a system without having to build it. Then we have generalist programming methods that we teach in our school. And above that, we have domain-specific high-level abstractions. For example, dedicated language for a specific application domain, such as artificial intelligence or radio astronomy. There is a gap in the middle, and this is the black duck of the family, which is the middleware. The middleware is everything that you need to make the software work on top of the hardware. And you need an operating system, a compiler, a runtime manager, and such things. And finally, on top of all of this, there is one last thing, which is the applications that the user is designing. And on the right of the slide, you can see a few design levers that you can play with in order to optimize the behavior of an embedded system when you are developing it. But what do you want to optimize? Let's step back. The main design drivers, the main design objectives that you have to optimize are efficiency. You want to optimize the latency of the system, the throughput, its energy consumption, or its quality of service. This is one driver. Then you have the safety of the system. Is it real-time? Does it have real-time constraints? Is it verifiable? Do you have a way to test the system that you have developed? You also have security as a key issue nowadays. Is the data that is handled by the device secured or not? We also have the cost, of course. How much does it cost to build and to design this embedded system? How much does it cost to upgrade it? How much does it cost to maintain? And one very last important objective is the sustainability. How much CO2 will you emit when you build this system? How much CO2 will it consume during its lifetime? And what is its environmental or societal impact? All of these are key objectives that you want to optimize. But the issue is that the optimization of any single of these objectives is very complex. It's a Rubik's Cube on its own. And one issue on top of it is that when you try to improve one objective, for example, when you want to increase the sustainability of the device that you are developing, you are very often increasing the cost of the device that you are building, which is a bad thing for you. Even worse, if you focus on efficiency, so if you just focus on one objective, you have sub-problems to solve. And when you try to optimize the latency, you will most likely increase the energy consumption of the system, or you can also increase the resource usage. So there is no simple solution for this optimization. Okay, so what are the key design challenges that we are facing today? So the first one is the explosion of the design space. We have seen that there are many things to optimize, and each one of them requires a few configurations that you can explore, that you can try. And if you combine the exploration of all these sub-configurations, you end up with a design space that is completely huge and that is impossible to explore exhaustively. A second issue is that, as I already almost said it, there is no optimal solution. If you have a set of configuration of your embedded system where you try to measure the sustainability of the system and the cost of the system, where you want to maximize the sustainability and minimize the costs, you will see that there is one configuration with the best sustainability and one configuration with the best cost. But there is no global optimum. If you want to find the best configuration, you need to look for the Pareto front or Pareto optimal solution, which gives you the best trade-offs between all configurations that you can achieve with the design of your system. Okay, so here the challenge is that we need powerful methods and tools to automate and accelerate the exploration of the design space, which is too big. Okay, my work mostly focused on three contribution axes that I'm going to develop later. The first one is about model-based computer-aided design for high-performance embedded software. The second one is about approximation as a design lever for system design. And the last one is ultra-low complexity artificial intelligence. Before we present these three axes, let's open a parenthesis about my academic career first. Okay, so throughout these last 10 years, I had the chance to collaborate with many research groups in France during different research projects, mostly funded by the National Agency for Research. And this gave me the opportunity to work with a few public laboratories all around France, and also with a few companies, mostly in Brittany, but also in Paris and in the south of France. I also had the opportunity to work with partners all around the world, and in particular with a few academic partners. I am only listing here the fruitful collaborations, so collaborations that led to publications or the submission of a project, or a collaborative project, and also a few companies abroad. Okay. Throughout these years, I had the opportunity also to co-supervise a few PhD students. First, on the model-based computer-aided design axis, I had the chance to co-supervise 5 PhD students. On the approximate computing design levels, I had the opportunity to co-supervise 2 PhD students. And finally, a more recent topic of research is the low complexity AI, which is a topic where I co-supervised 3.5 PhD students. During these years, I also had some teaching duties, and on average, I taught 220 hours per year. These teaching were mostly done at INSA Rennes, the school I'm working in, but also at the University of Rennes, our neighbors, and in the Universitat Politécnica de Madrid, in INSA Euromed in Fès, in Morocco, and in the University of Clermont-Auvergne in Clermont-Ferrand. During these teaching hours, I had the chance to instill a bit of a research topic in my teaching, notably with the course on parallel programming for embedded multiprocessor system on chips since the beginning of my career, and more recently about the use of Tanguy program graph for artificial intelligence since 2021. Then I also had to assume some responsibilities during these years, and on the local level and on the administrative level, I am responsible currently for the 5th year of the electronic and computer engineering department, and before that I was responsible for the 3rd year of the INSA Euromed student visiting Rennes for 1 year. Then on the local level, I am an elected member of the administrative board of the IETR laboratory and of INSA Rennes. And on the team level, I am the organizer of scientific seminars for the research team I'm working in, the team, and I organized more than 160 seminars since 2017. On a national level, I am participating in the animation of the GGR SOC2 of the CNRS. And on an international level, I am participating in many conferences, including the Samos conference, where I created a special session for negative results. I was chair of the DASIP conference in 2022, and I'm taking part in many other conferences and reviewing for international journals and many conferences. This closes the part on my academic career. And so now we go back to the scientific side of the presentation. So first, we are going to focus on the first contribution axis, which is the model-based CAD for embedded software. And I'm going to focus on a specific contribution about the influence of Dataflow moldable parameters on optimization criteria. Okay. So first of all, what is the motivation behind this work? When you do the design space exploration for an embedded system, you have this kind of workflow where you start from an application model, you go through a design space exploration framework or compiler, and you generate some code or some hardware that implements your system. In each step of this process, you have many things to do. For example, during the design space exploration, you need to perform the resource allocation, and you need to run some optimization heuristic to try to improve the behavior of your system. On the target side, there are still many things that you can do. You can play with the dynamic voltage and frequency scaling. You can change the scheduling policy of the computations, or you can select your own hardware, if you can build an ASIC or if you can use an FPGA. And then last but not least, you have the application side. On the application side, there are many things that you can do as a developer of an application. You can select alternative algorithm for the same objective. You can select how to represent the data that your algorithm is going to manipulate. And you can specify the degree of parallelism of your application. Through all of these design levers, you can optimize many things. We have already seen them: the latency, the throughput, the energy, the memory, and the quality. Okay. And what I'm interested in this contribution is what's on the left. Usually, when you want to explore some alternative configuration of an algorithm, the developer will try different solutions manually and sequentially one after the other. Here, our objective is to enable the explicit modeling and exploration of alternative algorithm specifications, to expose it to the design space exploration framework. Okay, so how does it work? The work is based on the Synchronous Dataflow model of computation that was proposed in the 80s by Edward Lee. In this model of computation, you have a set of actors which represent computations and that can receive some data and produce some data tokens on input and output ports, respectively. This data token, this data, is transmitted from one actor to the next through a set of first-in, first-out queues. And the execution of such a model of computation is data-driven. The availability of data will enable the execution of the following actor. Okay, so for example, here, the split actor is producing enough data to trigger 2 executions of the sovereign. Okay, now we can update this model and replace the scala, the integer production and consumption rate of the actors, replace them with expressions. So we introduce some parameters. So here, for example, the height and the width of the image processed by the algorithm, and the degree of parallelism. And we replace the integer production and consumption rate with some expressions that depend on these parameters. And by resolving this expression, we can once again find how many times each actor is executed. Okay, this model is very friendly for the design space exploration. It exposes discrete actor firings, so discrete execution of functions that you can map and schedule and pipeline on the different cores of your architecture. It also exposes FIFO first-in, first-out buffers, which are also discrete elements that you can map in the memory and that you can allocate in the memory of your computing system. And the last thing is that here you have parameters, but if you want to change the value of these parameters, for example, to explore different degrees of parallelism with parameter n, you need to change this parameter manually and rerun the design space exploration framework. This is what we propose to change. So what we have introduced is what we call moldable parameters, where you can specify a set of alternative values for each parameter of your Dataflow graph. So here you have the height and width and the degree of parallelism parameters, but you can also introduce Boolean parameters to switch on or switch off some pipelining stages of the processing that you are specifying. You can also introduce frequency parameters that will impact how fast the clock of the system will run when running the application. Okay, with this very small example, with just a few parameters, we already have 192 configurations that we can explore and that we have explicitly specified with this model of computation. The parameters that we have created are, for some of them, functional. So, for example, the height and the width of the image impact the size of the result and the resolution of the images that you are going to process. And you also have some non-functional parameters, parameters that have an influence on the design space exploration, on the degree of parallelism, on the clock frequency of the system, but that do not impact the actual output of the algorithm. Okay, how well does it work? To try to test and experiment with this idea, we have used this design space exploration flow, where we start from the Moldable synchronous data flow graph, very simple model of the architecture, just enumerating the cores and the memory of the system, and timing information, profiling information about the actors to know how much time it takes to execute an actor on the core of the system and how much energy you will spend when you execute one actor on the core of the system with a given frequency. You give all of this to the design space exploration tool, which in our case is the Prism rapid prototyping tool. And this tool will select the value of the parameters, apply some graph transformations on the data flow graph, perform the mapping and scheduling optimization, allocate the memory. And from all of these steps, you can obtain the metrics that you want. So you can obtain the latency, the throughput, or the memory footprint of the system with a specified set of parameter values. For when you run this design space exploration exhaustively for all configurations of your system, you can obtain in the metric space, you can obtain all the configurations of your system, and you can identify the configurations that give you the Pareto front, so the best trade-offs among all configurations of your system. Okay, how well does it work? We experimented on a set of applications, of image processing applications, including a Sobel filter, a SIFT key points detection, and a stereo matching algorithm. These three applications have very different sizes, and in particular, they have a very different number of configurations, with 500 configurations for the smallest one, and more than 10,000 configurations to explore for the largest one. And the first very interesting result is that very few configurations lead you to a Pareto optimal configuration. For the small application, only 21% of all configurations give you an interesting trade-off. And for the largest applications, less than 2% of the configurations give you a Pareto optimal solution, which means that if you try to find this Pareto optimal solution manually, you have a lot of configuration to explore before you can find, unless you have a good intuition, before you can find one of these interesting trade-offs and one of these best trade-offs offered by the system you are developing. Okay, now the bad news is that this is taking a lot of time. To obtain these figures, we have run an exhaustive design space exploration where we run all configuration and we evaluated the metrics on all configuration, which took more than 6 hours for the largest of the three applications. So it's taking a lot of time. So how can we do better? To do better, we can use the following idea. First, we start from the design space where we have all the parameters values that we can explore. And we can select a few values, not randomly, but we can select a few values. And for these values, we will see how good they are in the metric space and what are their latency or their memory. Then from this information, we can try to classify what is the impact of a given parameter on any of the metrics that we are observing. So for example, here I can try to classify the effect of an increase of parameter 1 on the latency of the system. And I can classify it, I can identify it, and I can see that each time I am increasing the value of parameter 1, the value of the latency metric is also increasing. It's also possible that the increase of the parameter value will cause a decrease of metric value, that it will have no clear effect, or that it will have no effect at all. And the idea is to try to identify what is the impact of each parameter on each one of the classification metrics. From this information, we can go back to the design space, and with this information in mind, we can try to find the set intelligently. We can try to find the set of Pareto optimal parameters that will give us the Pareto front of the metric space. Unfortunately, we did almost all of the work, but not all of it. The classification works. So we have shown that it is possible to identify the effect of a parameter on the different metrics of the system, but we were unable to close the loop and go back to the design space and to the metric space, which is something left as a future work. All of this has been implemented in the Prism Rapid Prototyping Framework, an open source framework, and has been published in Tacit 2022. Okay, this closes the work on the first contribution. Now let's switch to the second one about approximation as a design lever for system design. And the contribution I'm going to focus on is about lossy image compression for machine-to-machine communications. Okay, what is a machine-to-machine communication scenario or use case? On the left, we have a camera, which is capturing image of its environment. And these images are sent to a vision algorithm, which is in charge of analyzing the image and retrieving useful information. Nowadays, most of these vision algorithms are powered by artificial intelligence algorithms. Okay, now let's see in a bit more detail how this works. On the left side, we have the IoT device. These embedded systems that are capturing images are most often Internet of Things devices that run in the street, for example, for observing pedestrians. And what you have is that you capture a raw image with this camera. Then this image can go through some processing done in the IoT device that will help enhance the quality of the image, or that will help pre-process the image to ease the work of the vision algorithm. And you obtain such an image which is pre-processed. Then this pre-processed image goes through a lossy encoding algorithm whose purpose is to compress the data and transform it into a stream of bits, a bit stream, literally, that will be received by the processing facility, where it will go through a decoding process before being fed to the vision algorithm. Here, something important to see is that when you go through the lossy encoding process, you are voluntarily discarding some quality of the image in order to save some bits in the bit stream. And so the image that you reconstruct on the processing facility side is a distorted image with compression artifact. Okay, what are we trying to optimize here? Here, the first thing that we want to maximize is the accuracy of the vision task. We want the vision task, the service that we are providing to the user, to have the best accuracy possible. At the same time, we want the size of the bit stream that is transmitted over the network to be as small as possible. Why? Well, simply because when the bit stream is larger, you have more data to transmit, this costs more, and especially it costs more energy on the side of the IoT device. So you want to minimize the bit stream size in order to minimize the energy consumption at the bit stream size. The bad news here is that as soon as you reduce the size of the bit stream, you also lower the quality of the image. And because the quality of the image is lower, the accuracy of the vision task tends to decrease also. So this is a trade-off that you have to find. One last thing that you want to do is that you want to minimize the complexity of the computations that you are performing on the IoT device side. Why? Once again, for energy. The higher the complexity of computations, the higher the energy consumption of the system. The bad news, once again, is that if you reduce the complexity of the computations, this will tend to reduce the effectiveness of the edge processing or of the lossy encoding, which will increase the size of the bit stream, which is something you do not want. Okay, so what did we do in this context? Oh, yes, and finally, image quality. I don't know what image quality is in this context. There is no clear, well-defined metric of what a high-quality image is when you are talking about an artificial intelligence algorithm. Most human can say if an image is beautiful or not. An artificial intelligence, we don't really know. Okay, first work we did on this topic is about vision task accuracy. And to understand the work we did, we have first to understand how you train an artificial intelligence algorithm. The traditional way to train an artificial intelligence is to start from an original image and to train a neural network. So basically what you do is that you give this image to a neural network. This neural network gives you a prediction of what's inside the image. And then from the ground truth, so you know what is in the image in reality, you will try to minimize the difference between what is predicted by the artificial intelligence algorithm and the ground truth, so what is actually present in the image. And using this information, you go back to the neural network, you try to correct its weight in order to obtain the best prediction possible. This is the traditional way of training an artificial intelligence. Then what happens when you have compressed image? You have an image, a distorted image that was compressed, for example, with the JPEG algorithm. What you can do is that you can train another artificial intelligence, or actually the same network, but you are training it with different data. You feed this network with distorted image, and you try to minimize the difference between the prediction of the network on the distorted image with the ground truth. Why do you need to do that? You need to do that because if the original network was never exposed to the distorted images, it was never exposed to the compression artifact, its resilience to the artifact will be quite low. And actually, if you give directly these images to the original network, as we will see later, the quality of the prediction will decrease very rapidly when you start introducing a compression artifact. And the contribution that we did is that we proposed an expert training solution where what you do is you take the same network, but instead of just minimizing the difference between the prediction on the distorted images and the ground truth, you minimize both the difference between the prediction and the ground truth and the predictions between the difference between the network prediction and the predictions made by the original network on undistorted image. So here, the idea is to try to force the network to have the same behavior as the original network, which was working on undistorted, pristine images, but now you want to enforce this behavior on distorted images. Does it work? To try to assess if this idea is working, we implemented it with the DeepLab V3 Plus network, which is an image segmentation network. So trying to find the position of the different objects in the images. And what we did is that we exposed the different types of network to images with varying qualities. And the different qualities were obtained with the JPEG compression algorithm. Okay, we measure the quality of the image as the number of bits per pixel of the transmitted images. So the higher the number of bits per pixel, the higher the quality of the transmitted image. And we measure the quality of the accuracy of the vision algorithm as the MIOU, the mean intersection over union of the algorithm. And the first thing that we have to know is that if you give raw uncompressed images to the original network, you obtain an MIOU of 80%, approximately, at the cost of 9 bits per pixel. Now, if you give distorted images to this original network, which has never seen any distortion in the training set of the network, then results are not so good because you start for the best quality of a compressed image, you start with an accuracy of around 50%, and then you go down when the quality of the images is lower. When you use the fine-tuning algorithm, the fine-tuning training method, results are much better, and you are able to recover of most of the loss that you have with the distorted images. And finally, when you use the expert training method, you have an even better result, where the accuracy of the network is higher for the different quality of the image that you are giving it to it. Okay, what are the main messages of the result here? The first one is that you need to specialize the network if you know that this network will be exposed to distorted images. Okay, because otherwise the result will be very poor, the accuracy of the vision task will be very low. And you can use fine-tuning or expert tuning, but you need to train the network specifically on the distortion it will see when it is used. The second message is that we did quite well. The expert training method that we proposed is able to increase the accuracy of the of the network for the same quality of images that are sent to it. And we have a 6.8% better BD rate, which is a metric used in the video compression community. Okay, so to summarize this part, what did we see? We see that we have proposed a technique to improve the accuracy of vision task, and it was published in Electronic Imaging 2022. We also have proposed other contribution in this context. One contribution that we proposed in MMSP 2022 is a contribution about selecting the appropriate image resolution before compression and applying some selected pre-processing before going to compression. And we, during the PhD of Alban Marie, we also studied how to integrate this process within the codec configuration, within the encoding process, and also what could be an objective metric for the quality of such a system. Now it is time to go to the last, the third and last contribution, which is about ultra-low artificial intelligence complexity, and I'm going to talk about Frugal reinforcement learning with Tanguy program graph. Okay, so what are the motivations behind this work? The traditional way to deploy an artificial intelligence on an embedded device is to start from a very big neural network and then to try to compress it using pruning, quantization, compression, or factorization technique. And you obtain something that is approximately 10 times smaller. Okay, this is the same network, but slightly different, but still the same. And the problem with this kind of network is that you still need a lot of processing to execute it. And you still need some kind of embedded GPU or some kind of a neural processing unit inside your embedded hardware to try to run this lightweight neural network. And this is what we want to change. Here, our proposition is that instead of using this flow, we should build a light by construction artificial intelligence model, and we should get inspiration from the genetic evolution of the nature. Okay, so what model are we using? We are using the Tanguy program graph model, or TPG for short, which is a model that was proposed in 2017 by two Canadian researchers, Stephen Kelly and Malcolm Haywood. In this artificial intelligence model, which is represented by a graph, the trained network is represented by a graph. You have the vertices of the graph that are called the teams. The leaves of the graph are called the actions, and the edges of the graph are called the program. This is a reinforcement learning artificial intelligence algorithm where the TPG will learn how to do something useful in an environment on its own with a reward mechanism. Okay, how does it work in inference? To understand how it works, we must first focus on what a program is. If we look at it as a black box, a program receives the current state of the reinforcement learning environment, processes it, and produces a number. If we have a look at what's happening inside the program, you can see something that resembles an assembly program where you have a sequence of instructions that take as a parameter some data from the environment or the result of a previous instruction. And the result of the last instruction is the result of the program, which will be called a bid. Okay, now let's take a step back and go back to the TPG structure. To understand how to run the TPG in inference, first we need to know that an action will be associated to each leaf of the graph. So here, for example, if we are playing the Space Invader video game, for each leaf of the graph, you will have a button that will be pressed associated to this leaf of the graph. How do we execute this TPG? First, we receive a new state from the environment, and we start the execution of the TPG from the root team of the TPG. So a vertex with no input incoming edge. We execute all the programs on the outgoing edges of this root team. We get a bid from each one of these programs, and we just identify the largest bid, and we continue the execution of the TPG with this path. So we go to the next team. We execute the program on its outgoing edges. We identify the largest bid, and eventually we will reach a leaf of the TPG, which is an action. So we execute this action on the learning environment. As a result, we receive a new state of the environment, and we can start a new inference of the TPG. Okay, how do we get the structure of a TPG? How do we train the TPG? We use a genetic learning process where we start with a set of random TPGs, and then through a natural selection process with mutations and crossovers and populations with discarded individuals, we obtain better and better individuals that eventually are able to beat the game that we are playing. How does it work? We use a lot of randomness for this evolution process as a natural selection process. And for example, randomness is used to mutate the topology of the graph, to change how the vertices are connected, and to change the content of the program, to swap instruction, add or remove instruction, or change the data they are looking at. How well does it work? TPG has been thoroughly evaluated in the PhD thesis of Stephen Kelly, and it has been shown to be a very efficient learner. So it is able to compete with the efficiency of deep learning network in deep Q learning network in 2017. And what's very interesting is that it has an adaptive complexity, which means that the size of the TPG that you are growing adapt itself to the complexity of the task that you are trying to solve. A complex task will lead to a complex TPG. By opposition, deep Q learning tends to have a fixed topology, which is decided by the developer when he starts training the neural network. Then you have a very fast execution. TPGs on the same hardware is 1 to 2 orders of magnitude, or 2 to 3 even, orders of magnitude faster than the deep Q learning, equivalent deep Q learning network. It is also very lightweight. A trained TPG requires less than 100 kilobytes of storage compared to a deep Q learning network that requires more than 50 megabytes. And finally, you have a great explainability for the TPG models because each program selects where it is looking at. So you have some kind of an evolved attention mechanism, whereas usually with deep Q learning, you need to do some post-training analysis to explain how the network works. Okay, what did we do? What is the contribution? We developed a framework, JJLATI, a Tangle Program Graph framework for training and inferencing Tangle Program Graph. The issue with this framework, one issue that we have is that because we need to support evolvable graphs, we need to be able to support the addition or the removal of teams or programs in the structure of the TPG. And this has an overhead on the performance of the system. Also, we need to be able to remove instructions to the program or alter program, which once again requires a flexible structure, which has an overhead when we manipulate the TPG, and also requires a software fetch and decode mechanism to execute the TPG. What we proposed is a code generation mechanism where we start from a trained TPG. So we have the already trained TPG. We generate some equivalent C code that implements the inference behavior of the TPG without the need for any additional third-party library and without the need for JJLATI, for the JJLATI framework. So we have the standalone C code reproducing the inference behavior of the TPG. Okay, how well does it work? We experimented this on 4 different platforms, ranging from a high-end Intel processor to a low-power Raspberry Pi 2 chip. We experimented with 5 different video games from the arcade video games. And what we measured is the speed up of the TPG inference with the generated code compared to the inference of the TPG with the library. And here we obtained very good results with a speed up between 20 times faster to 80 times faster on the laptop and on the Raspberry Pi 2 respectively. So the standalone C code is able to go much faster than the C++ code of the training and inference framework. Okay. Contribution summary about the TPG. So what I presented is a way to generate standalone C code for the ultra-fast inference of a TPG graph. But we also introduced the JJLATI framework for training and customizing TPGs. And this was published in TASIC 2021, where it received the Best Paper Award. And all of this is available once again on GitHub as an open source project. Okay, now that we have seen all of the contribution, it is past time to talk about what's ahead for me. What are the research perspectives? First, about first of all, about computer-aided design for software, embedded software. Here, one of the future objectives that I have is to try to work still in the data flow domain, but in the domain of radio astronomy. And why is it a good idea? Radio astronomy is all about stream processing and signal processing algorithm with huge real-time constraint. You need to process the data produced by an antenna as fast as it is produced. And this is something good because this is something that we know how to do with data flow models of computation. Then something that is a work in progress, notably with the PhD thesis of Ophélie Renaud, we are working to support gigantic data loads. So loads of data produced by the antenna are in the order of terabytes or petabytes per second. And you need to be able to run the signal processing algorithm on huge data centers where you have multi-node CPUs, GPUs, and FPGAs doing the processing. And so we need to make sure that the data flow system is able to program this kind of processing target. And the last goal of this work is to try to convince astronomers to use what we are proposing them. So basically, we have to convince them that data flow models of computations are efficient system to model their algorithm, and that they will be able to deploy their computations on multi-node GPUs using this kind of model of computation. Okay, and this work will notably be studied during a visit to the Swinburne University in Melbourne in Australia, which is planned starting in January 2025. Okay, then a second long-term perspective for research about software-based computer-aided design is to try to match dynamic neural network with reconfigurable data flow. Okay, what are dynamic neural networks? In dynamic neural networks, compared to classical neural network, the data path inside the neural network is not fixed. The data path is dynamic, and some data may be switched from one neuron to another, depending on what the data is and how well it will be predicted by the system. And this helps increase the accuracy of the neural network. It helps also increase its adaptiveness to different types of data. And it also helps lower the theoretical complexity of computations of the neural network compared to classical static neural network. The bad news is these neural networks are quite inefficiently deployed on GPUs, which are more efficient for classical fixed data paths. On the other side, we have reconfigurable data flow. Reconfigurable data flow is something that we have been working on for a few years, and it supports online design space exploration for data flow graph, where the data is also able to switch from one actor to the next, and where you can redirect data, change the topology of the graph dynamically while executing the application. And this is supported by the Spider runtime that we have developed in the team, which is able to support heterogeneous multiprocessor system on chips and very high performance targets. And this was mostly recently developed in the work of Florian Arestier's PhD. Unfortunately, we are lacking some applications to show the efficiency of the system and to show how well it behaves on multiple targets. And so we think that there is a clear match between these two paradigms, and that probably we could do something by using reconfigurable data flow to deploy dynamic neural network on embedded hardware. Okay, now about the approximate computing axis. One direction for future work in the short term is to work with the Witulo startup, which is a startup founded by Justine Bonneau, former PhD student I co-supervised. And the objective of this work is to try to use approximations and parallelization jointly for the optimization of low-power embedded software. So here what we want to do is to try to co-optimize the nature and the types of the data we are handling in an algorithm, and to co-optimize this with the SIMD instruction, the single instruction multiple data instruction, that implements the parallelism at the lowest level of the software stack. And here, the approach that we want to use is a transpiler approach, so a source-to-source transformation, where we start from some source code, we analyze it, and we generate some more efficient code using the appropriate data types, for example, with fixed point data, and the appropriate SIMD instruction. Longer term, let's say, objective is about the machine-to-machine communications, where there are many things that we can do. For example, we could study some other types of signals instead of video. We could study audio, biosignals, or multimodal signals. We could also work on the coding efficiency, try to integrate what we did during the past work directly inside the encoder, try to find an objective quality metrics for artificial intelligence algorithms also, for images fed to artificial intelligence algorithms. Energy is something that we can optimize everywhere. We can optimize it locally on the edge processing side or on the computing facility side. But the best way to do this is to do a global optimization of the energy process, because sometimes losing a bit of energy on the edge processing facility may enable you to save a lot of energy on the main processing facility. And so you need to have a global study of the optimization. Then we can also continue the work on improving the accuracy of the vision algorithm. And last but absolutely not least, this kind of system well deserves a global lifecycle analysis of the system to try to see what is the impact of each part of the system, what is the energetical, the environmental, and the societal impact of each part of this system on its environment where it is deployed. Last future work is the continuation of the work about Tangle program graph, which is already currently funded for the short term by the FOOTX project, which is an ANR project, and where we try to do a full stack optimization of low power artificial intelligence powered by TPG. Our main objectives are first to extend the capabilities of the TPGs, to try to integrate energy awareness as part of the training process of TPGs, and to also develop some ultra low power implementation on embedded devices such as microcontrollers or FPGAs. This concludes this presentation. And now, if you have any questions, I will be very happy to answer them. And while you are waiting for the questions, you can have a look at the completely irrelevant statistics that are displayed in the background of this slide. Thank you very much for listening.